Okay. So today the talk is on the embedding of linear hypersurfaces and the Zariski cancellation problem. So this is the plan of our talk. First we will discuss some notation, then we will state Zariski cancellation problem, then we will recall some definitions here, and then we will kind of show that K1 is cancellative, we will prove that K2 is cancellative, and then we will just discuss embedding problem, epimorphism theorem, Abhyankar Sathaye Conjecture, and I will just display some result concerning them, and at last we will see a counterexamples to Zariski cancellation problem for all n greater than, over positive characteristic. This is important, sorry. So let us begin by notations. Okay. So first, K will always denote an arbitrary field unless stated otherwise. N will always be a positive integer, arbitrary positive integer, and there is some, we will write Rn to denote n polynomial ring over R. Over R, and then there is another thing, transcendence degree of A over B. It is nothing but the transcendence degree of A and B has to be domain here. A contained in B, both domain. Then we define transcendence degree of B over A to be nothing but the transcendence degree of the fraction field of B over fraction field of A. Okay. And so these are the notations, and first let me state Zariski cancellation problem, ZCP in short. Zariski cancellation problem has a long history, but we will not discuss it now. It asks for any field K and any natural number n belongs to Z greater than is equal to 0, is K1 cancellative, Kn cancellative. That is, if B is an affine domain, affine K domain, such that B1 is isomorphic to Kn plus 1, can we say that B was K1 to begin with? B is Kn. This is the question, Zariski cancellation problem. We know that for n is equal to 1 and 2, the answer is yes. We will see a proof of both today. And for n greater than equal to 3, characteristic of K strictly greater than 0, we know there are counterexamples. We will see that today also. And for n greater than equal to 3, characteristic of K is equal to 0, the problem is open. There are
write down negative, positive.
Yeah. No counterexamples.
And for n equal to 1 and 2, yes, for any current.
Yes, for any field. Okay, so this is our plan. So let me start with some definitions first. So the first definition is of something called factorially closed. Okay, so A is a subring of a domain B. B is a domain. Then we say that A is factorially closed. closed in B if for any A B inside B but not equal to 0, A B belongs to capital A implies both A and B is in A. Not any one, it is stronger than that. If AB belongs to A, then A and B both belongs to A, but A and B has to be non-zero. And some kind of related definition is something called algebraically closed. Again, A subset of B, B domain, then A is called algebraically closed. Closed in B if for any B inside B there exists a polynomial with coefficients in A, polynomial in 1 degree with coefficients in A, such that B satisfies this polynomial, then B is inside A. Of course, we have to take something non-zero. Yes. So the immediate note is that if something is factorially closed, then it is algebraically closed also. A factorially closed in B implies A is algebraically closed in B. Okay, and the next observation is that if A is contained in B and B is a UFD and A is factorially closed in B, let me write shorthand FC, then actually A is a UFD.
Because A corresponds to some subset of the set of prime elements.
Yes, because this thing is very strong. Whenever we have something like that, we can come to A. So this is, and next let us recall the definition of exponential map. Okay, I will write the definition. So phi, a K algebra map. Okay, I should start with domain. It's better to start with domain. A be an affine K domain then a K algebra homomorphism from phi of u, suffix u, from A to A of u. A of u is actually u is indeterminate over A, which is equal to A of 1. Then a K algebra homomorphism of this form from A to A of u is called,
So is u a variable?
yes, is called an exponential map. If it satisfies the following two properties. Number one, that if I go from A to A of u with the help of phi of u, and then I go from A of u to A with the help of the evaluation at the point 0, and if I come from A to A with the help of identity, then they are equal. Yes. And number B is that if I go from A to A of u with the help of phi of u, and then I go from A of phi of u to A of phi u v, v is another indeterminate, with the help of phi of v for A and keeping u fixed, and if I go from here directly to u plus v with the help of phi of u plus v, that is another determinant and included there, then this diagram also commutes. These are the two corresponding axioms related to the G action on a affine variety.
So these two axioms should hold simultaneously, right?
Yes, A and B. Yes. Okay. But we will sort of use something else. So this definition, some kind of equivalent properties. This definition is actually equivalent to the 5 properties that I am going to write. So let me write equivalent definition. It says that again I need a K algebra homomorphism. Phi of u from A to A of u such that now I'm going to state 5 properties. They are also equivalent to these 2 properties. Number 1 is that such that I will write phi of A, it is a polynomial in phi of u, so I will denote the coefficients by phi to the power I of A. I runs from 0 to infinity and u to the power I. That is phi I of A is a coefficient of u to the power I. Such that number 1, this maps phi I from A to A. They are actually linear maps. I should go there. Number 2 is that phi I running from 0 to infinity are finite. That is, for a particular A, this set is finite. For every A inside A. Number 3 is that yes, phi.
What do you mean by finite?
I have to put include it inside A of u. I cannot have a power series here. I have a polynomial here. That's the reason. And phi 0 of A is equal to A for all A. Number 4 is Leibniz rule, that is phi I of AB is actually summation over phi I of A, phi j of B, and I plus j is equal to n for all AB inside A. And number 5 is that if I...
Number 4, phi I, what is the subscript? Up? What is
This one?
No, lower.
This one?
Yeah,
This is
what
A.
the index? What is the index there?
It is a coefficient of u in the exponential expansion that...
No, what is the name of the index?
I, right?
Yes.
Do you use I into senses here?
Oh, sorry. Forgotten. Sorry, it should be n, yes. Sorry. Yes.
Please write a little bigger.
Okay. Sorry, yeah, this is my mistake. Phi of m of AB. This will split as coefficients here. M. Now this is okay, right? Yeah, thank you. And if I apply phi of I, phi of j to A, I will get back something like this. There will be a coefficient, and then it will be I plus j of A. Now in characteristic 0, this coefficient is well behaved, but in positive characteristic, it is not so well behaved, and that is the problem. So just note, if characteristic of the field is K and D is a locally nilpotent derivation, maybe I should write Q is contained inside A. And D is a locally nilpotent derivation on A, then the corresponding exponential map phi d is as follows. So I will have to define phi d from a to some a of u, and it will take a to a plus d1 of a, that is d of a first, and then 1 by 2, sorry, there should be a u, d of a u plus 1 by 2 factorial d square of a u square, and in this way.
So you claim that this is an example of an exponential map.
Yes, corresponding to a LND, because LNDs and exponential map are same inside characteristic zero fields.
So you
So
say
you
that
define,
they are the same.
You define exponential map axiomatically,
Yes.
but it turns out that all of them have this form.
If Q is
Characteristic
contained,
is zero.
is contained.
This is strongest in characteristic zero, if you contain rational number.
You said that it's enough to be characteristic zero, but that's
Yes,
not true.
because we have started with an affine K domain, so it's
If it is an algebra over some field of characteristic zero.
okay. So this is now we will move towards some properties of exponential map. I will need them later, so maybe I should write it down. Let me delete it and then write it down. Some properties of exponential map. So, some properties of exponential map. Okay, first we will start with A is an affine K domain. A is an affine K domain, and then and phi from A to A of u be a non-trivial exponential map. I will define what do you mean by a non-trivial exponential map in a minute. Maybe I should define it. We already are here, so let me define something called ring of invariant. Ring of invariant of an exponential map. It is denoted by a to the power phi, the exponential map, and it is defined by all those elements a inside a such that phi of a is equal to a. That is, the name suggests, it does not move a at all. And corresponding to this definition, we say phi is non-trivial if a is not equal to a of phi. Something is happening, and then we have two invariants. One is known as Markov-Leonov invariant of a. It is defined as the intersection of all ring of invariants for all exponential maps on A, and there is another invariant known as Duksan invariant of A. dk of A, it is called Duksan invariant of A, and it is defined as the smallest subalgebra which is generated by all the ring of invariants of all the non-trivial exponential map. So if A has no non-trivial exponential map, then this dk is actually just k. So now we have defined what is a non-trivial exponential map. So we have an affine K domain, we have a non-trivial exponential map, and we take something called, now we consider all these degrees, okay. Now we are defining again something. Let us call degree of u of phi u of a. Okay, that is the highest coefficient existing. Let us define it to be.
Bigger.
Oh, sorry. Yes. U degree of phi u of a. For any a in capital A, we define it to be something called phi degree of a. Okay. And we denote this same number by degree phi of a. It is not
Degree of
a.
small l.
Yes. Small a is any element, and this
In
is.
the middle, you wrote capital A.
Sorry. Thank you. Phi degree of small a. Yes. And so let us take. Let x be a minimal element with respect to this phi degree. Phi degree to this phi degree except the elements of a phi. It is actually local slice in LND, but here we are not so sure.
Except, you meant except.
Sorry. Thank you. So we will be taking all the phi degrees of A such that A belongs to A but not inside the kernel, and then we will be taking their minimum. And this will be attended, and let me denote this number to be by m, and this is attended at some x, and we are calling this, we are taking this element x. It is who has attained this minimum. So now,
How does it involve x?
so this minimum will be attended at somewhere, right? I am picking one and calling it x.
So this is just reformulation of the definition.
Yes. Because it's good to work with 1x. I will write some theorem, but it will be true for every x who has this property. So number one property is that a of phi is factorially closed in A. Number b is that transcendence degree of a phi with respect to k is equal to transcendence degree of k of a minus 1. Okay. And next, the C is actually local slice theorem in positive characteristic. That is, first take this C, we defined C to be phi m of x. That is, I am taking the highest coefficient of x, phi of x inside A of u. And this will be an element of the kernel because x is minimal. It cannot occur outside the kernel, otherwise it will contradict the minimality of x with respect to this. Then A inverted, A with C inverted is equal to A phi with C inverted x. And this is actually equal to A phi with C inverted 1, and this everything is happening inside fraction field of A phi of x. This is a theorem.
Give an example that this m, the minimal degree, is bigger than 1.
We can make it 1 actually. We will write next step. We will make it 1. Given any exponential map, we will do something to the exponential map, and then we will get another new exponential map for which we can assume m to be 1. I will.
But it is possible only in positive characteristics.
Yes. In
okay. Yes. I'm
Yes.
sure. I know this example. Okay. Thank you.
yes.
In the property C, x is the element of
Yes.
above, right?
Yes. Same element. Yes. So now we are here. Yes. Okay. Number D is this. Now, if transcendence degree of k of A was 1, that is, this becomes 0, then actually a phi is nothing but k tilde, not k. We have to take the algebraic closure because this is factorially closed, hence algebraically closed. Algebraic closure of k in A, and as expected this kernel will be k tilde and A will be k tilde of 1 because this C is now inside k tilde and it is a field. So this A will be nothing but k tilde of 1. And
And also one more request. We speak Russian English,
Yes.
and you speak another type of English.
Yes.
So please try not to speak with Blackboard, but with us, and pronounce words separately so we can understand.
okay, trying. So let me do it. If transcendence degree of A is 1, then the ring of invariant will be k tilde, and it is nothing but the algebraic closure of k in A, and hence with the help of this local slice theorem we will get A to be k tilde of 1. Okay, now number E. Number E is this. Number E is that we can actually take M to be 1 without loss of generality. So given this exponential map, we can construct an exponential map tilde from A to A of U such that the ring of invariants does not change, and with respect to x, this definition is just x goes to x plus c to the power some integer into u. Yes, this is the definition, but this n has to be chosen carefully, and for that we need affineness.
So what do you mean by a delta?
Another exponential map. Another exponential map. We can construct another exponential map such that the ring of invariance does not change, and this becomes actually m becomes 1 here because this is just this.
What is C here?
C is same.
C.
C.
is C.
Yes.
So this is
Yes. So I will give a proof of this thing in a minute, but let me just complete it. And it says that if S contained in A to the power phi minus 0 is a multiplicative closed subset, then we can extend phi to an exponential map Let me denote it by S inverse of phi, whose domain of definition is S inverse of A, and it goes from S inverse of A to S inverse A of U such that S inverse phi A by S. Now the elements are from S inverse of U, so they are from A by S. It goes to just phi of A by S, where A is an element inside A and S is an element inside S. Moreover, we can also write the ring of invariant, that is S inverse A, S inverse phi is nothing but S inverse of A of phi. That is whatever we are expecting, we will get that.
So these were some generalities on exponential.
Yes, so we will use it and prove our cancellative result. Only this much result I think will be okay. Now we will need another one, but we will just state it too much. So I will give a proof of this number 5 because it's easy, and let me just prove number 5. So we have an exponential map from A to A of U Okay, and x is the minimal element with respect to this phi degree. Now we have A is affine, so A is of this form k a1 a2 ar for some r greater than equal to 1, and now A is again contained in this ring, A of phi of C inverse of x. So we can choose n big enough such that C to the power n of ai's, they will be now elements inside this A to the power phi of x. Okay. Now we are going to define delta from A phi C inverse of x to A phi C inverse x of u. And how will we define it? We will just we will keep all the elements of A of phi intact. That is, delta of A is equal to A for all A belongs to actually A phi of C inverse this ring, and we will just move x accordingly. That is, we will define phi x to be x plus C inverse n of u. Okay, now this will be an exponential map here. Delta is an exponential map here. On A phi C inverse of x. Okay, and now if we just look at this set, that is delta restricted to A, then we will see that it is restricting to A of u, because that is by choice. N was here only. So delta restricted to A is an exponential map. Such that A of phi is equal to A of delta, and delta of x goes to x plus C to the power n of u. And we can take m to be 1 from henceforth. Okay, so let me now delete it. Okay, maybe I can write it here. So now let us recall a result by Abhyankar, Ikin and Heinzer. Okay, they have said that if R is a UFD and A is a domain, such that transcendence degree of A over R is equal to 1, and R is contained inside A and A is contained inside a polynomial ring with respect to R, and R is contained inside A, contained inside Rn for some n greater than equal to 1. If A is a factorially closed subring of this Rn, then A is actually equal to R of 1. Yes. And with the help of this result, we can show that K1 is cancellative. So let me now this is a corollary that K1 is cancellative. So for K1 is cancellative, we have B an affine K domain. Affine K domain such that B of 1 is equal to K of 2. So we have K contained in B contained in K of 2, and transcendence degree of B with respect to K is 1. It follows from here. Now the only thing that remains to show is that B is factorially closed subring of K2, and this follows because and we can actually write it like this, and B, let me write it, BW is equal to K of xy, right, from here. So we can just consider this LND, or sorry, this exponential map del W from K of xy to K of xyu. And for this exponential map, the ring of invariant will be B actually. So this will imply that B is factorially closed also. And so with the help of this theorem, we can conclude that B is K1.
And how do these authors prove this result?
Sorry, sir?
How do this Abhyankar and other people prove this result?
So this is a tough result. This is a tough result. This is not an easy result. Using.
Try to understand the proof.
Yes, sir, but it's long. It's not short.
But some difficult technique, or this is somehow
No
étale cohomology.
No, sir. No étale cohomology. I understand the proof, but it's long. Yes. Yes. It's a long proof. So, actually, sir, this is not even the most general result. You can replace UFD with HCF ring. They have used something called HCF ring, and I have just written it for UFD for our understanding. So this proves that K1 is cancellative. Now we will show that K2 is cancellative. Okay, let me delete it. So for K2 is cancellative, it was first done by, I think, Miyanishi, Shugi, Fujita for characteristic zero field, and then Russell extended it to perfect fields. But then it was stopped after for some time, and then Macalenauer and Cresciola gave a proof for algebraically closed field, which was an algebraic proof. The previous proofs were very involved, and they used I think cohomology, something like that, and they gave a very simple proof. We are going to look at their proof, and with the help of their proof, Nina ma'am and Bhattwadekar sir, they gave the complete proof. That is, for any field, K2 is cancellative. So we are going to look at the proof given by first Cresciola and Macalenauer, and then we will extend it. So next theorem is that K2 is cancellative for any field. So our first case 1 will be, we will assume K to be algebraically closed. So case 1, let K be algebraically closed. Okay. So it is given that B is an affine K domain. Maybe I should transfer the notation to A. A is an affine K domain such that A of 1 is equal to K of 3. This is given, right? So we have to show that A is K2, and we have assumed K to be algebraically closed. So now we can consider A to be a subring of K3. Oh, sorry, there is another result. Wait. Okay, let me just, sorry. There is another result by Macalenauer and Cresciola that we need, and it says that if A is an affine domain, such that it is rigid, that is ML of A is equal to A, then ML of A1 is also A. That is, nothing non-trivial can happen here except the del x exponential map. This is the result we will need. Now we have considered A to be a subring of K3, and this thing implies that ML of A1 is equal to ML of K3, which is K. We all know that. Which is equal to K. So this implies that with the help of this result, ML of A cannot be A. ML of A has to be something non-trivial. This implies with the help of this result, ML of A is not equal to A. This implies that there exists a non-trivial exponential map on A. There exists a non-trivial exponential map on A, and
I don't understand what's the connection, what you say with this result.
Sir, I am saying that here ML of A was K, and that implies that ML of A is not equal to A, because if ML of A was A, then ML of A would have been A, which is not true.
It's not obvious that you have a rigid.
So there exists a non-trivial exponential map on A, and now we are in this situation. So we have K, which contains A to the power 5, which contains A, which is contained in K to the power 3. Okay, now again A is A1. So this implies that A is again a ring of invariant for some exponential map of K3. A is ring of invariant for some non-trivial exponential map on K3. This would imply A is factorially closed in K3, and this is already a non-trivial exponential map, ring of invariant of a non-trivial exponential map on A, and A to the power 5 is factorially closed on A. So this would imply that A to the power 5 is factorially closed on K3. Now we
Again lost. Why A is a ring of invariants of some non-trivial exponential map?
Because sir, we can write AW is equal to K of 3, right? So we can take this non-trivial exponential map from A of W to A of W U, where every element of A goes to A for all A element in A, and W goes to W plus U, 1 into U.
But it has nothing to do with the previous. Why do you have this arrow? So you have this 3 inclusions, right?
Yes. Yes.
And from these 3 inclusions, you conclude that A is a ring.
No, sir. Sorry. This is not the conclusion. This is actually something plus and.
Something additional.
Yes. Because I want to use Abhyankar, Ekin, and Heinzer. So I will be somehow trying to prove this is factorially closed. Because then I can write this to be K1, because this transcendence degree is 2. So I cannot apply Abhyankar, Ekin, and Heinzer. I have to come down 1 to 1, and then I can apply it. Okay. So this is factorially closed. Now I can apply Abhyankar, Ekin, and Heinzer, and because transcendence degree of A to the power 5 is 1. By Abhyankar, Ekin, and Heinzer, A to the power 5 is actually A of 1. Let me call it K of Y. And this is inside A. Okay. So now we are in this position. Now we are going to take local slices. Okay. So we know that there exist without loss of generality. Actually, without loss of generality, we can assume that this phi has a minimal element z such that the degree is 1. This is property 5, such that the phi degree of z is equal to 1. Now, among this minimal element, we choose z0. We choose z0 such that the y degree of phi 1 of this z0, because now minimal degree of this is 1. This would imply phi of z is equal to z plus phi 1 z of u, right? And this phi 1 z is an element of a of phi, and a of phi is here k of y. So I am choosing all those z1 z such that this phi 1 of z y degree is minimal. That is, we choose z0 such that the y degree of phi 1 z is minimal. Okay, and then our claim will be that this is actually a. That is, a is nothing but k of y and this z0. These two are enough for k, but we will prove it. Till now we know that k of y z0 is contained in a. So we will show that.
I didn't catch you. Why we can assume that degree of z equal to 1?
So given any exponential map, we can change the exponential map. And
Without changing the kernel,
and
Cherenkov invariant such that we have this.
This is this punct.
yes, property 5. Yes.
Okay.
Okay, and after going that, we are again choosing among this minimal elements such that the y degree of phi of z0 is minimal. To choosing, and so, okay, so if we'll prove in the contrapositive way that if possible, suppose there exists a which is in a but not in k y z0. Okay, now by the local slice theorem, a is contained inside a phi c here is actually this phi inverse z0, sorry, phi 1 z0 inverse z0. Yes, and this phi is nothing but k of y. So this is k of y z0 with some element inverted, 1 by phi 1 of z0 inverted. This is inside this, and this thing is inside k small, this is small k, this is k of y z0, because this element was inside a to the power phi, which was inside k0. So this is inside fraction field of y, ky z0. Okay. Okay, if possible, there exists such an a. Now a is not inside k of y z0. Therefore, a should look like this: some polynomial in y z0 by actually, let me name this element. Let me call this thing, I should name it. I should have named it. I should name this before. Let f be defined as this phi 1 of z0, because we are going to use it. So these things become f inverse, this thing also become f. So now we are here, and it is inside a phi, just to be sure, which is ky. Okay, So it will be of this form, f to the power r for some r greater than equal to 1. We can delete this. This ways. Okay. Now we are in algebraically closed field. I am using this. I can split f into, f is an element inside K of y. So I can split f into product of linear factors, that is y minus lambda i's for some finite i's, and then I can just product y minus lambda i's with every I except one. Let me call it I belongs to I except one j and into a, and this becomes f of y z0 by y minus lambda j. So this thing remains, and this is again inside a. So now my denominator looks good. It's y minus lambda j. Now again I can split this thing, y minus z0 y minus lambda j, to be some polynomial in y and z0 by dividing, and some polynomial in just z0 y minus lambda j. This is also inside a and this is also inside a. So we can conclude that g1 z0 of y minus lambda j is inside a. Okay. Now we can write this again into linear factors, and it will be like z0 minus mu i's for some i's y minus lambda j. This is inside a, and now I can write this thing as a polynomial in z0 minus just mu 1, right? I can do that, and y minus lambda j. This is again inside a, and this would imply that, let me write this polynomial. It was summation some ci z0 minus mu 1 to the power I runs from 0 to some some s, and this is y minus lambda j. Okay, this is inside a. Now I can manipulate this polynomial like this, that is,
what do you try to prove?
so I am okay, let me show my last step. So
that a is not in K of y.
no, so
So
we will,
contradiction.
yes, so I will, my last claim is that z0 minus some L into y minus lambda j, this should be inside a, something of this form.
And if this is the case,
Then we can apply phi over it, then phi of z0 minus L by y minus lambda j will be of this form, z0 minus L by y minus lambda j, this is inside a, so I can write it, plus f by y minus lambda j. F was, this thing came as was there inside f, so I can again write it of u. Okay, and now the y, now look at the y degree of f by y minus lambda j. This is strictly less than the y degree of f, but we have assumed f to be minimal of such.
okay, so contradiction.
Yes, this is the contradiction.
Contradiction with what?
So that we have chosen f to be such that the f has minimal degree. F has minimal degree, f has minimal y degree such that phi of this z is of this form. Now I have given some new z, phi of this is of this form, but the y degree has decreased than f, but by our choosing, that is the contradiction.
I see a contradiction, but we should conclude that this is a polynomial in two variables. How do we conclude?
So we have started with, if possible, there exists an a.
So we assume that there is something outside of the polynomial.
And
Yes.
what is the problem if f have degree 0? Because you just decompose f by this error multiples, but if degree of f is 0, you cannot do this. Is it possible?
Yes. But if degree of f is 0, then it's inside K, right?
Why? Yes, yes. So it's inside K. Why it's not possible?
But if it's this inside K, then this is a polynomial in
This is just a
yz0, but then
polynomial,
it's
okay.
here. But A was taken to be something not in here.
Yeah.
So degree of, and this thing will follow actually from the fact that this A is algebraically closed here. We will write a polynomial of this thing and A is algebraically closed, so P of this B is 0 in A, so we will be coming back to A. So I was trying to write the polynomial explicitly.
Okay.
So I think this is not necessary, right? I can move on.
It's not clear.
Yes, okay. So now the next case. Let me.
So it gives us quite explicit proof of the cancellation problem for in dimension 2, but modulo this difficult result of these three answers, right?
Sorry?
So this is a complete proof of cancellation problem for two generators.
Yes.
For in
But
dimension 2.
yes,
But modulo this result of Abhyankar.
Mo and Suzuki, Abhyankar, Ikin and Heinzer, and this we have used some result here.
And also,
So this is not tough. This is actually easy, but it involves another technical homogenization of a exponential map. But this result is easy, but that
Isn't
result
it,
is tough.
We know this result
Yes,
at least in characteristic 0, but it's
Yes.
the same in positive.
Almost the same idea. But this result is, yes. Okay, so now let us move on to the non-algebraically closed part. Okay. Here also the idea is, maybe I should not delete it, wait. We can just, now the case 2. K is any field. So it is given here. Now again the same idea is worked. We will land here that A phi is ky of A, and we will again assume these things that this is of, no, but there is, okay, wait, there is a little trick. We will come from here. Up to this everything is same. Okay, we have used everything, but here we will assume this z0 from above and then we will come down. That is the trick. Okay, let me delete this part. Okay. Now we already know that this is true for algebraically closed field. So we have A1 is equal to K of 3. So this implies that A tensor K of K bar of 1 is equal to K bar of 3. K bar is algebraic closure of K. Okay, so we can get it from here, and by our case 1, this implies A tensor K of K bar is K bar of 2. Okay.
Ananya, 20 minutes.
Yes. Oh. Okay, so maybe I will just finish this proof and leave it. Or maybe, sir, I can leave this proof, and because it will almost.
This is not the main part.
Yes.
It's better to understand how the counterexamples to cancellation
Yes,
problem.
yes. So let me leave it, sorry. And it will again follow the same trick and we will again arrive. Okay, let me just write the steps. So for step 1, we will consider this exponential map. That is, we will extend this exponential map to k bar from this thing a tensor k of k bar of u, and then we will consider this z0 here, and then we will show that this k bar of z0 y, we will get something like that a bar, that is a tensor k of k bar will be of this form, and then we will be able to modify this z0 and get some g inside a such that k bar g of y is equal to k bar z0 of y. Okay, but g and y are now inside a, and then we will use faithfully flatness to deduce that. We'll get something like that, and then we will use that k bar over k is a faithfully flat extension. Such that will be a faithfully flat extension, and then it will imply that a was nothing but this k of gy, but we need both of them inside a. z0 was taken from a bar, it was inside a bar, that is a tensor k of k bar. Here we could not have applied our faithful flatness, we needed something in g inside a, and then we will be able to apply faithful flatness and get this result. So this is the step. So let me just rush to epimorphism theorem and counterexamples. Okay. Now there is a related problem of epimorphism. Okay. An epimorphism problem and related conjecture known as Abhyankar Sathaye's conjecture. Okay. Epimorphism problem asks that if we have a is every closed embedding from this kind of, is every closed embedding rectifiable? That is, if we have a embedding of this form, that is a mk goes to a nk, sorry, we call it phi. Does there exist an automorphism alpha of this n, a of n, such that alpha compose phi becomes a linear embedding? This is the question, and in ring theoretic form we studied like this, that let me write just this special case that I will talk about, where m is equal to n minus 1, that is the difference between n and m is 1. It asks us that if h is a polynomial in k x1 up to xn such that k x1 up to xn by h is equal to k of n minus 1, does it imply that h is a coordinate? This is what we mean by epimorphism problem related to linear hypersurfaces. So it is a special case of epimorphism problem or embedding problem, and the first positive thing was called the epimorphism theorem, and it was given by, I think, Abhyankar, Mo and Suzuki. They said that yes, if characteristic of the field is 0 and n is equal to 2, then the answer is yes. But we need these two things. And what will happen in positive characteristic? It was already known. If characteristic of the field is strictly positive and n is greater than equal to 2, then there are counterexamples. And one such counterexample is this. Let me take f to be this thing. Characteristic of the field is p. So f is z p to the power e plus t to the power s of p inside k of z t, where e and s both are greater than equal to 2 and p does not divide s. If I take such a polynomial, then it can be shown that k of zt by f is equal to k of 1. That is, this part is satisfied, but f is not a coordinate. And this f also extends to all the higher, that is, if I, this is also true actually, x and zt by same f. Now inside here, this is obviously equal to n plus 1, and f still remains a non-coordinate. Okay. So this is the epimorphism theorem. Now in positive characteristic, it is already known that it's non-true, but in characteristic 0, there is no complete answer except for n equal to 2. That is, starting from n greater than equal to 3, there is no complete answer, but there is a conjecture that yes, it is true. This is a conjecture that is not yet proved, and we have done some discrete positive cases of this epimorphism problem and this Abhyankar-Sathaye conjecture in characteristic 0 and in characteristic p, arbitrary characteristics. And that
you have a counterexample, so what is the conjecture?
No counterexample, affirmative results.
This counterexample is...
These are in positive characteristic, but that doesn't mean everyone is a counterexample.
The conjecture is for the 0 characteristic.
Conjecture is for the 0.
Sorry. Yes. Conjecture is for the 0 characteristic. And
for m bigger than 2.
Yes.
Because
Yes, otherwise it does not have a meaning. Yes.
Because for n equal to 2, it's proved.
Yes, n equal to 2, it's proved.
Yes, now it's good.
Okay, so now let me display the results, because, and it ultimately led to the counterexample of the Zariski cancellation problem. They are related, kind of. Okay, so let me write the rings quickly. So C is my ring, that is x1 up to xm yzt by alpha x1 up to xm polynomial in y minus f of zt minus product of some primes. I will define it. H is a polynomial in mzt. Okay. CV such a linear hypersurface. We call it linear hypersurface because this is linear in y, and this thing is PI's are actually all the distinct prime factors of alpha. of alpha. With such a C, we started our result, but let me write, I can delete this now because I don't need it. So the first result is of characteristic 0. So let me call it theorem. It says that first characteristic of the field has to be 0 plus if alpha has a prime factor of degree 1. That is, this P is there is one P which appears just once in alpha. If this, or there exists some Pj such that Pj divides H. Here, I don't know, but here for this theorem we have to assume that one Pj divides H. Then we know that the following are equivalent. Then the following are equivalent. First is that, let me call this thing H, this hypersurface. This is a coordinate. And this is equivalent to that A is an affine space. That is, epimorphism problem is satisfied for this. And number C is that this small f is a coordinate. And number D is that A is stably polynomial will also do. Sorry. Yes. These are the equivalences in characteristic 0. Now we also consider in arbitrary characteristic. K is any field. But here we need to take a special form of alpha. I will write a very special form of alpha for understanding quickly that alpha is of this form. A1 xm up to am xm. That is product of polynomials of these forms where ai's are elements of k of 1 for all I such that each ai has one separable multiple root. That is, there exists a root of a1 such that it is multiple and separable in the sense that k of that root over k, this is a separable extension. And I need such roots for every ai. Then the following are equivalent. Okay, number 1, same. H has now transformed. Alpha is of this form just. First 3 are same. A is a polynomial ring and F is a coordinate. But the fourth for arbitrary characteristic demands something more, that only being a stably polynomial is not true, is not enough. We need something more. And ML of A is equal to K, or decay of A is equal to K. A, that is either ML is trivial or decay is trivial. So in characteristic 0 we don't need it, but for arbitrary characteristic this D has to be changed, otherwise we don't know what will happen. And from this theorems, it follows that if we take such a B, if we take such a B, let me give it a better notation. Let me call it A, G1, Gm, F. Okay, where Gi's are polynomials in K1 and F is a polynomial in K2. Then from this theorem it follows easily that if F is a non-trivial line, that is K of ZT, that is, it is a counterexample to the epimorphism problem in positive characteristic. The same A, that is, this is 1 and K of ZT is equal to K of F not equal to, sorry, F is not a coordinate. It is a non-trivial line.
The first condition means that this is a line, right?
Yes.
And the second one is that it is not trivial.
Yes, it is not a coordinate. Yes, that's the. So if it is a non-trivial line, then by this theorem, we know that this is not true, so this is not true. Then now this A G1, but we need all those things, that Gi has some separable multiple root. No, we just need this. Sorry, let me write. Gi has some multiple root. We don't need separable. Then we can just consider this in K bar. Okay, and then we can conclude with the help of this theorem that this is not affine space above, and this implies this is not affine space below. Okay, but there is another theorem, and this is by Nina ma'am, and it says that if this thing is okay, is a line, this F is a small f is a line, then actually this A is one stably polynomial. This is again, I understand it, but it's kind of constructive. She has constructed this automorphism, so it is isomorphism. Okay, so this two theorem says that this is a counterexample to the Zariski cancellation problem, but here m has to be greater than equal to 1. So we get from this the Zariski cancellation counterexample to the Zariski cancellation problem. Problem in positive characteristic, because non-trivial line does not exist in characteristic 0 due to epimorphism theorem. For all n greater than equal to 3. And we have some isomorphism result also, which says that if I take two A, G1, G2, Gm, F and H1, H2, Hm, F of this form, that is A, G1, G2, Gm, comma F and A, H1, H2, Hm, comma F, same F, okay, and such that Gi's and Hi's have multiple root, one multiple root, have one multiple root, then if the roots of G1 with multiplicity, that is considered the root with multiplicity, does not match with any Hi, the roots of the number of roots, sorry, so we are just considering the number of roots of G1 with multiplicity, and it does not match with any number of roots of Hi with multiplicity, then they are non-isomorphic. So now we have non-isomorphic counterexamples of Zariski cancellation problem. So let me give the a family of non-isomorphic counterexamples to the Zariski cancellation problem. Consider this family: x1 square, x1 minus 1 to the power r, x2 square, xm square y minus f is the same thing, z to the power p to the power e plus characteristic of this field is p greater than 0 plus t to the power sp, such that r, e and s all are greater than equal to 2 and p does not divide s. If I consider this family, then every member is a counterexample to the Zariski cancellation problem, and of course for n greater than equal to 3, and no two members are isomorphic.
So if we consider polynomials in one variable over this algebra, we will obtain polynomial algebra.
We will not obtain polynomial algebra.
We will obtain.
If we add one more thing.
Oh, sorry. So this is stably polynomial algebra. Not, I mean that this is not isomorphic to A of something. But if I add one variable, then it will become isomorphic, stably polynomial.
Okay, you have finished?
Yes, I think.
Can I ask the question? Because this is somehow black boxes for us, and as far as I understand that we need to prove two things. The first one, that a ring of such form is not isomorphic to a polynomial ring, and the second is that when we add
one or two or any
variable, then it became isomorphic. So, as far as I understand, the first part, that this is not a ring of polynomial, is proven as Dirksen invariant is not the whole ring. This summer we'll try and to
yes,
understand Nina's paper,
Yes,
and she just understand that Jackson invariant is not the whole ring. This
Yes.
is the first part. And the second part is unclear for me, how to prove that if we add a variable, then we became polynomial ring. Is it just explicit exponential map with a slice or something
No.
else? How to
No,
prove
no.
this?
Okay, the proof
But let's show on the bracket what to prove. This,
this,
we
right?
ask about this, right?
Yes, he's asking about this.
Just the main idea.
Okay, she has explicitly constructed this. That is, suppose, let me call it A for
Just
now.
explicit
Yes.
form of isomorphism.
Yes.
It is not
As far as
with exponential maps.
No, it is explicit. She has constructed some f which goes from here to here, and then some g which goes from here to in the reverse direction, and then compositions are identity. It is explicitly constructed.
So just establish an isomorphism.
Okay.
Yes, it does not involve slice
And
theorem.
this is written in
Ad,
Niels' paper.
yes, advances paper. This is written. I know. Yes.
Okay.
And this is explicit construction. And when I asked ma'am how to construct it, I don't know. She didn't explain it to me. She said it has to be
I
constructed,
think
but
that it's a little bit more convenient not to prove the isomorphism, but to have an exponential map with a slice. But okay.
I think we tried it and it did not work out. Yes. We were also unable to prove this thing with the help of slice theorem.
Thank you.
Okay, any more questions? Okay, if not, then we can turn off this nice device.
Thank you for your time and patience, and I'm very sorry.